My name is George Androulakis and I'll speak about optimality in quantum data compression using dynamical entropy. This is a joint work with Duncan Wright. So let's recall the best compression rate via asymptotically invertible encodings. We have a quantum source that emits symbols, strings of quantum symbols. We have an encoding E that takes those strings of quantum symbols to a storage device, and the decoding D that takes those compressed strings of symbols to a receiver. So the quantum source consists of a symbol set S of normalized, not necessarily orthogonal vectors of some d-dimensional Hilbert space Hs, and a sequence of random variables x sub n with values in S. So the quantum source produces finite strings, tensor products of symbols x1, x2 up to xn, and that belongs to the S to the tensor n, which is a subset of the Hilbert space Hs to the tensor n. And each such string of symbols is produced with certain probability. And if the sequence xn is i.i.d, then we say that the quantum source is i.i.d. The domain of the encoding E as well as the range of the decoding D contain tensor products S1 Sn in S to the tensor n, which is a subset of Hs to the tensor n for every n, or more generally, states on the Fock space generated by Hs. By this symbol, I denote the Fock space generated by Hs, and here I recall the definition of the Fock space generated by a Hilbert space. The encoding and the decoding are completely positive trace-preserving maps. The compression rate, how do we define the compression rate? We take a string of n symbols, we apply the encoding E, and then we take the dimension of that state, where the dimension of a state is the number of its non-zero eigenvalues. We multiply it by the appropriate probability. We sum up for all string of symbols, and we strings of n symbols, and we divide by n, because we want to find the number of qubits needed per symbol. And we take the limit as n goes to infinity. We call that Re, but we assume, this is important, that we assume that an efficient decoding D exists. So by that I mean that if I compose the encoding with the decoding for any string of symbols, string of n many symbols, and I average with the appropriate probability, and I sum up for all strings of n symbols, and I take the limit as n goes to infinity, that average fidelity goes to 1. And the best compression rate is the infimum of R sub E when efficient decoding D exists. Schumacher in 1995 proved that for an i.i.d quantum source, the best compression rate is equal to the von Neumann entropy of the average state. So now let's examine a different definition of the best compression rate via indeterminate-length encodings. These indeterminate-length encodings were defined by Schumacher and Westmoreland in 2001. So we start with the Fock space generated by the two-dimensional Hilbert space. We take PL, the projection to the Lth component of that Fock space. We multiply the PL by L, and we sum up, and this defines the length observable. This is an unbounded self-adjoint operator on the Fock space generated by the two-dimensional Hilbert space. And using the length observable, we can define the indeterminate length of every state rho on the Fock space generated by the two-dimensional Hilbert space. So how do we define now the best compression rate using the indeterminate length encodings? So we consider not arbitrary encodings, but uniquely decodable encodings, and we assume that these encodings take values in the Fock space generated by the two-dimensional Hilbert space. With this formula, we define the average length of E of Sn for a uniquely decodable encoding E. And the best compression rate is then defined by taking the infimum overall uniquely decodable encodings E of the average length of E of S to the tensor n, and we divide by n because we want the number of qubits per symbol, and we take the lim sup as n goes to infinity. Okay, so that redefines the best compression rate using indeterminate-length encodings. So now, how do we compute the best compression rate? We take the average state of S to the tensor n, we compute the von Neumann entropy of the average state of S to the tensor n, and this is close to the infimum of the average length of E of S to the tensor n. Infimum overall uniquely decodable is close to up to distance 1. But that distance 1, when we divide by n and take the lim sup as n goes to infinity, that distance that goes to 0. So for any quantum source, not necessarily i.i.d, the best compression rate is equal to lim sup 1 over n of the von Neumann entropy of the average state S to the tensor n. Practical considerations. How do we find the best encoding? If we know in advance how many symbols we are going to emit, then a quantum version of the Shannon-Fano encoding or Huffman encoding will actually give the best encoding. And this can be shown using a quantum version of the Kraft-Macmillan inequality. There are several versions of Kraft-Macmillan inequality in the literature. Our version is an if and only if statement. So let's recall now in the third part of my talk, recall the dynamical entropy of a quantum dynamical system. First, recall what is the quantum dynamical system and what is the transition expectation. Quantum dynamical system is a triplet of a von Neumann algebra, a dynamical map from the von Neumann algebra to itself, and the state on the von Neumann algebra. Accardi defined the quantum Markov chain to be a tuple of a state and the transition expectation, E. A transition expectation is a linear bounded positive unital map on MD tensor A to A. So how is the quantum Markov chain corresponding to a quantum dynamical system defined? So we have a quantum dynamical system and the positive operator measure gamma, and we define the quantum Markov chain phi and E. Phi is the same as the state of the quantum dynamical system. The transition expectation is defined via this formula where we take the operators a.i.j, which belong in the von Neumann algebra A, we sandwich them with the appropriate elements of the positive operator value measure, and we sum them up, and then we compose with the dynamical map theta. We define the quantum Markov state psi of the quantum Markov chain by iteratively applying the transition expectation to more and more elements of MD. The joint correlations of the quantum Markov state is defined as the sequence of density matrices that defines that quantum Markov state. And the dynamical entropy of the dynamical system with respect to the positive operator measure is defined as the lim sup of the von Neumann entropy of the joint correlations divided by n, the lim sup of that. So our theorem examines lossless quantum data compression of not necessarily i.i.d quantum sources and relates the best compression rate to a dynamical entropy of an appropriate quantum dynamical system. We Given any quantum source, not necessarily i.i.d, we construct a dynamical system, a quantum dynamical system, and the positive operator measure gamma such that the joint correlations are equal to the average state. Therefore, the best compression rate of that quantum source is equal to the quantum dynamical entropy of the quantum dynamical system that we construct. The construction is given in my slides, so you can see the construction. My slides will be available in my website and in the site of APS. And also, at the end, I give the link to the paper. Thank you.